and mathematical modeling, applied math, and core math. And of course, I'm at the end of the core math. Now, the problem with these equations is like the weather or something. They're so complicated you can absolutely never solve them. So forget about it. So what, as a pure mathematician, what you can really do, I think, is only phenomenological studies of such systems. So you can try to extract the essential features and solve those. That's about all you can do. And that started then with Lorentz and Henon first. Who simplified the equations and did some computer graphics and saw some strange things. So you can, if you look at the system, for example, you can have some periodic attracting orbit, and then it bifurcates if you change the parameter and get some periodic order 2 and so on and so on. Or they could find also some strange compact sets. Oh, it's not working. There's a red light at least.
That one's okay to put the other one on also.
Oh.
This one is for the, this is for the room.
All right. So, 2 pockets. Oh. Oh yeah, okay. Thanks. It's better? All right, so okay, so what I want to talk about then is to attractors, to actually try, I mean, what mathematicians can do, as I say, is to do some phenomenological studies. And then the easiest thing to do is to start with something really low-dimensional, where you really can understand something, prove something or disprove something. Of course, once you get up to more complicated things like Navier-Stokes 2D, already it's, well, at least I don't think it's known yet whether they have strange attractors. They have attractors, it's known, I guess, but not strange ones. It's not known. So that seems to be really hard. So I'll stick to very low-dimensional stuff. So first I remind you there are various ways of defining attractors. So I'll choose one. Standard by Real. Define it.
How you use this concept and applied setting? I mean, what aspect of it would be useful to know?
What would be useful to know? I guess how attractors. Well, let's see. What would be useful to know? It would be useful if you want to understand the climate. If you could know something about attractors. I don't say that that what I will say will tell you that.
I mean, just what sort of things?
But it would be a question of bifurcations of attractors, maybe.
Somebody in climatology wants to know.
What they would like to know? Well, what about whether attractors really exist? I mean, the computer graphics indicates, of course, and there are some results, but do they really exist, mathematically speaking? That would be a phenomenological thing. That's what I was thinking. Okay, so let me get down to definition. Real. So a definition would be first pseudo-orbit. So X is a compact metric space. And epsilon is positive. Then if you have an orbit of some mapping, or almost an orbit, xi is epsilon, and epsilon pseudo-orbit. If the distance in some metric between the next point and the previous, the image of the previous one is not too big. So this is standard definition. And with that, you can say that you can define a relation that says that x is can fall from a point can fall from to y if for every epsilon there is a pseudo orbit, epsilon pseudo orbit from x to y, or x is equal to y is included as a case. And then we say that we have an equivalence class, meaning that it consists of those y, so that you can go both from x to y and from y to x with epsilon pseudo orbits. So that divides the if you have a compact metric space, divides it into compact equivalence classes. And then you can define in the obvious way what it means for an equivalence class to be larger than another, can fall from one to another. And then you can say what are the minimal orbits, and those are what I will call attractors. An attractor is a minimal equivalence class. All right, they always exist. That means you can. It means you cannot fall from that place to another equivalence class by pseudo orbits. And the simplest examples are attracting periodic orbits. They will be the simplest examples of attractors.
This definition depends on it being non-reversible, doesn't it?
Why?
Well, for one thing, if F were homeomorphism, this
F could be a homeomorphism.
this relation is symmetric already.
No.
Definition.
Is it?
By uniform continuity.
Well, you can still have a homeomorphism with an attracting fixed point.
Huh?
I think it is.
So then what is this? Yeah, I don't know.
It's not an order relation, it's just equivalent. It's two equivalent.
Well, I mean, if you have a linear map on R, x goes to 1/2 x. 0 is an attractor. It's the only attractor. All right. So I just want to remind you of first of what's known about attractors in.
Sorry,
Yeah.
I just don't understand the definition. What is a minimal equivalence class? I mean, I think of equivalence classes as being a partition of the space. So I don't
Minimal with respect to this ordering.
Yeah, with respect to this ordering, right?
Maybe
Yeah.
ordering. Maybe you explain the ordering.
So that kind of,
Right. So, for example, take any.
symmetric relation if it's a homeomorphism?
No.
Yeah, but I mean,
You can't go backwards always. Every point in space can land on a minimal attractor. Every point. But you can't go the other direction.
Yeah, what's the order relation? Because I see the equivalent.
What? So what is this relation? It means that x is larger than y for any element x in x and any element in y.
But according to this definition, you see if for every epsilon there is a pseudo orbit from x to y, how about y to x?
Well, yes, if you could do that, then it would be in the same equivalence class, yeah. It would be in the same equivalence class.
That's going to give an example.
All right. Yeah, thank you. That's right. So we have a mapping. This all points can fall here down to this point. This is an equivalence class. This is an equivalence class. Points here are, well, a point here is in an equivalence class by itself because it says x can be equal to y as a case. But it will fold into here, and then it can fold further into here. This is not minimal because you can go from here to here. This is an equivalence class, but it's not minimal. It's not attracting a whole neighborhood to it. It's just sucking a whole neighborhood to be an attractor.
So even if f is invertible, putting the epsilon in makes it seem non-invertible.
Oh.
The point can go from there to there, but it can't go back to there.
Oh yeah, that's right. Yeah. That's right. Yep. So okay. So what's known about these attractors? Well, first of all, this picture here is the one-dimensional case. So if you have a polynomial p of x of degree d, it's a theorem by Guckenheimer that you can only have d attractors, at most d attractors. They don't have to be attracting periodic orbits. They could be like the Feigenbaum attractor would work, I think. It's a contour set. So it can be contour sets. If they are like that, they have to always contain a critical point. That's a fact. Okay, so that's the R case. On the other hand, if you go to the next step up, you go to the complex numbers. They're the only attractors. The only attractors are attracting periodic points. Attracting periodic orbits. Plus infinity, maybe. Include that. So the situation is different, remarkably different between R and C. And I think the picture, maybe to say why that is not so strange, because you can imagine you have a polynomial on R, and interval, which is serves as a trapping region in the sense that the interval is mapped into itself in the reals. Then obviously you can have a very nasty thing going on inside here. But if you look at it in the complex, it's not really, you should maybe draw something like this and think of it as having an attracting periodic orbit here. And this is just part of the boundary. And then you think, well, the maps on the boundary is part of the Julia set. The maps, you expect them to be chaotic on the boundary. That's fine. So that's not, maybe that's a sort of a picture to see the difference between the reals and the complex in this case. Why? It could, well, actually, I just do something like this. I don't know, whatever. It can hit the boundary in some contour set, maybe. Hit the reals in the contour set, perhaps. Yeah. So let's see let's see what's the story with the Feigenbaum. Then you have one critical point, and I guess in that case that sits in the contour set, and the rest, I guess, is probably just the complement is, I guess, the whole Fatou set. See. C minus the counter set, I guess, probably.
No,
Huh?
the whole interval belongs to the Julian set. The whole interval, not the counter set. Okay.
Is that true? Yeah, that could be. Yeah, that could be.
You see the basin for
Yeah.
polynomials, the basin of attraction is simply connected.
Not the basin of infinity.
Not the basin of infinity.
Yeah.
Is it
I'm not sure. This might be the point at infinity. I'm not sure. I haven't looked at this particular case, but I can imagine it could be the basin of attraction of infinity, complement being a counter set. That's. I don't know. I don't know. I don't know. That doesn't sound right. Well, it doesn't sound right because you have a trapping region.
If you have a point on the real axis, which is a real attractor, then it must be either complex attracting or parabolic. So
Oh, yeah. Yeah.
So it will certainly attract something complex.
Mm-hmm. Well, let's see, but there's the thing, if you have the Feigenbaum attractor, the critical point is in it. So there cannot be any other, it cannot be any other another basin. I don't know. I don't want to get into this theory. I just.
So the Feigenbaum set is not an attractor in this sense.
In the real, in the complex. That's why it's an attractor. It's not an attractor in the complex. There's a difference.
But so the point is that something which is attractor on the real may fail to be an attractor in the complex.
Right. Yes, that's what I want to say. Yeah. That's right. Yeah. That's right. Exactly. Whether what exactly the shape is here, it's something nasty, anyways. Whatever it is. Okay. So if you go to P1, it's a little bit different than C, but there's only one possibility in addition, is the attractors are attracting periodic orbits. Or P1 itself. To say that the whole of P1 is an attractor means simply there are no attracting periodic orbits in space. You could have other Fatou components like Siegel disks and Hermann rings and parabolic things. Those are fine. They don't destroy the fact that the whole thing is an attractor. Typically, if you have a Siegel disk, you rotate it around. Since you have epsilon orbits, you can just migrate to the boundary and move all over space. So it's the thing that happens there. All right, so it's not so difficult. The next step up would be R2. And there you have the, well, I guess this has been talked about quite a lot, the Henon maps. As the simplest example, the ones that have degree 2. And Henon found some parameters where it seemed to be an attractor. A was 1.4, I think, and B is 0.3. Something like that. But that was only about computer experiments. Nothing rigorous about it. What? So anyway, you can to draw a picture, because that's sort of typical. What happens when you look at attractors? You have some region, and then xy goes to x, comma by. You make it very thin, and then you make it thin and you bend it, stretch it by adding the other terms plus a minus x squared, so that becomes like this, and then if you stop there, you see it's still quite trivial dynamics because x is preserved. So it's just a map inside each vertical line. So it's just a linear map on each line, and x is constant. So it's not very interesting. So you add another your rotation, 90 degrees, to flip the coordinates. And if you have the parameters right, you are inside the original box. And then, so then you have the situation up there. You have a trapping region mapped into something smaller. And then you can imagine maybe even you get laminations in here, and you keep repeating the process. All right. So now, finished with that. Let's in C2. Then there are only attracting periodic orbits. So again, they disappear when they move from R2 to C2. So in that case, it does sort of probably draw more or less the same picture. That they disappear. Okay. Now, let me move to P2, so that's where I really want to be. So P2, as you know, is the set of complex lines through the origin in C3. Or it's compactification of C2 where you add a line at infinity. Okay, so I had the following theorem with Weikert. Saying that the attractor can be either it's small or it's somehow very large. Suppose, so here I will look at, this is on P2, so F is a holomorphic mapping on P2. So, and we suppose that we have an attractor for this mapping in P2. Then well, let's go back to P1. In P1 you can have a periodic orbit, or it can be all of P1. So X is then well, let's see, then let's say, okay, then 1 X is an attracting periodic orbit. Or B, it could still be the whole space. But you can also have something that is in between. I can't say it has to be something like a P1, but I just don't know. But we know something, namely X contains, actually, this will be redundant, but it's just for easier to write it down this way. X contains an entire image of C. So it could be, for example, a complex line. But maybe not. We don't know too much.
There's a holomorphic map of C.
Contain a non-constant. Yeah. So there's a holomorphic mapping from C to the attractor, containing the attractor. So, yeah, maybe I should just give an example first, because that's an easy to see trivial case. Just have to take F. So you write P2 as C2 union a line at infinity, and then you take F from P1 to P1 has no attracting orbit and no attracting periodic orbit. And then you extend it to F from P2 to P2, and you can extend it as, if you can do that in many ways. If you extend it as a homogeneous polynomial from C2 to C2, then all stuff that have a large norm gets mapped further towards infinity. So it is then clear that P1 is an attractor. So you have this case where you can have the third case happen. Right. Okay, so the proof is not too long, so I can give it.
If you take a set of such mass to C, and the attractor is that F act on it or something like that?
Does it mean small f?
This big F act on
On the attractor? Yeah, it will be surjective map from the attractor to itself.
you
Yeah.
get more received by moving them around somehow?
It's not clear how many copies of C you will have in an attractor. We don't know too much. We like to say we will have this. Yeah, we would like to say we have that as a possibility. The problem is to have some kind of solenoidal thing, but the problem is in cases to rule. Yeah, to rule out the attracting orbits inside an attractor. Don't kill it. So, excuse me?
So you can't change the rotation of P inside it. Because you have P. P is just move P around. So small level.
Right. Yeah, you can move P around. We might move it out of the attractor, but I don't know if you can move it inside the attractor. Oh, you can compose with F, but it's not necessarily sure that you get another copy of C. All right. Excuse me?
It's the holomorphism of it inside it. You can change the rotation.
Yeah. Oh, yeah. You can compose with things, but that doesn't necessarily mean that the image changes. Okay.
Examples of through when the attractor is equals with the images.
Excuse me, that one?
Examples of a through when the attractor is strictly bigger than the image of C.
Oh, yeah. You can have, because you can have it equal to P2.
No, but
No, I don't think so. We don't know. We don't know this. We don't know.
lamination.
Well, yeah, this is mainly the example. We can have some. We don't have many examples. We have the straight lines and like CW equal 1, something like that. But
They're all closed.
they're all nice, closed. We have not been able to find.
Any crazy.
Not been able to find a solenoid.
You do have examples where it's not just a P1 or...
No, we haven't been able to find that, no. So one of our conjectures is maybe there aren't any, but I don't know. We have not been able to show it's would be algebraic, say. Just don't know. Can't decide. All right, so to give the proof, you need a concept of attracting sets. It's just slightly different. K is an attracting set if K is the intersection of some shrinking neighborhoods. So K is an open, K is compact, K is inside an open set, and F maps that set into itself. So it's essentially the same as an attractor, except it could a priori be, for example, if an attractor is a limit set of attracting periodic orbits, then we won't be able to find that. We need this larger concept, which is slightly larger than attractors. You can think of them as perhaps sequences of attractors converging to a limit attractor, perhaps. All right, but it's nevertheless easy to see that if K is an attractor, it's almost an attracting set. So if K is an attractor, you can certainly write K as a decreasing limit of attracting sets. Ki attracting. That's easy to do. So, and then we will actually try to rather put C's inside attracting sets. That's a little easier. But then you have to take some limiting procedure. So we say suffice to find a C in a K attracting set. All right, so okay, so let's see. Now, so we have this notation: K is in U and F of U is inside U. So now let A be a collection of linear maps on P2, affine automorphisms. Of P2 and close to the identity. In some precise sense. First of all, since you have this stability property here, you have that if F is in A, we can use L is in A, then L composed with F should map U to U. That's easy because F maps U in relatively compact in U and you can perturb a little. It's okay. And also if PQ are close, there exists some L, call it LPQ, close to the identity mapping P to Q. That's easy to arrange. And and we also want to find a small number. Pick T is slightly less than 1, so that if A could be a whole open neighborhood of the identity, so that if P is in P2, there exists some LP in that neighborhood. Fixing it is P, and the derivative is scaling by 1 over T, I guess. So it just expands a tiny little bit. Oh, this doesn't work. All right. Okay, so now suppose you have P in K and some high iterate is close if in this sense, closer than some little distance is close to P, then you can close up the orbit and do some slight perturbations of the iterates by putting in some expansions in the middle. First of all, you have to close up the orbit. Is that what I call it? The Q. Then let's see. Then the previous point was you want an expansion. So you just throw in expansions at every step. They don't change the orbit. So you just close up the orbit and you have thrown in expansions at every step. So, and the orbit is closed. So now you have a mapping from the set to itself. A map that sends U to U, and it takes P back to P.
So maybe you have big perturbation now.
It's yeah, because you have put in many perturbations, but every time you do that, you start in U. This composition is in U. So the next composition will be in U. This will be still in U. You never escape from U because you only compose self-maps of U. You compose such maps from U to U. So if you start in U, you stay in U.
Don't you have two L's?
Yeah, this map, whatever L you put in here from that class, that neighborhood of the identity, you're going to land in U. So whatever you compose with in that class is going to be fine. So we're going to compose with many different ones from that class.
You also want it to be expanding.
Yeah, and also expanding. Right. So think of it as, yeah, think of it this way, that the map is think of it as like a saddle, that you have contraction this way towards the set, but expanding along the set. I think that's the picture of what goes on. So since you use the maps F, you compress towards K, and then you can expand along K, fine.
But that was probably scaling by 1 over T.
Right. So that's actually scaling in the sense it actually expands. Yeah, that's true. But since if you take a point and you apply F, you are already down here somewhere close to K. And then you are allowed to expand because you can expand a little bit again since you are already deep inside U by that time. So you can expand here, and that's fine. It means that the compression towards K should be stronger than T. You should think of it that way, I guess. So think of it as a saddle set where the stable derivative is smaller than T. Then it wouldn't be a contradiction. what happens here is that there are two cases.
Are you using something about holomorphic things to say that something is attraction?
Not yet, but I will. This is nothing, no, there's nothing about holomorphicity yet, I don't think.
I don't understand. I mean, you've given detailed description here, but just too many.
Yeah, I know. It's,
Too many sentences. I don't know
right,
what's going on.
right. Well, you can think about the polynomial map on C2, the example of that, where you have a homogeneous polynomial on C2, and the attractor is the line at infinity. Whenever you apply the map, and the neighborhood U is just the complement of a large ball. When you apply the map, that ball expands a lot, and you get very close to the line at infinity. If you then compose with the linear map, which is like multiplying by 2 or something, that's not going to destroy that. You're going to still stay far out, close to infinity. And when you repeat the process, you're going to even much, much closer to infinity, and so on. So there are two cases. If you look at this, some derivative, some eigenvalue of the derivative of b prime at p is larger than 1 in absolute value. So that's the expanding case. In that case, what is the picture? Oh, here's U and P, and then there is a direction. You might even assume that it's a saddle point, for that matter. Easily arranged. So there is actually the map B from P to P, from U to U. Self-map with an expanding eigenvalue at the fixed point. So the way you can think about it, now you have an unstable manifold, but you can think of it also that you have a mapping from the disk to this thing. Wow. That the image of that, and then actually if this is a unstable manifold, actually then you can see, of course, when you iterate B, you're just expanding it, and what you should, if you think of the attractor, you should think of it more or less like expanding, but being compressed to be inside U. So it keeps expanding, but along K. We don't say it's contained in K, though. We can't say that, but it's contained in U. And it keeps expanding more and more in U and along K, if you think of it that way. So this, you have to then repeat this process for smaller and smaller attracting sets in smaller and smaller neighborhood. And if you can keep having these copies of C, you can pass to a limit. And for this, you need a Brody trick, you can call it. Pass to a limit to get a map phi from the unit from C to the attractor. That means you have to do some rescaling and so on, but never mind. There is a way to pass to a limit if you have a sequence of copies of C. And that gives you a copy of C and it will be in the limit in the attractor. Yeah, okay. The trick is just that if you have a complex manifold, and if you have a if you have an image of the unit disk inside a complex manifold M, and it has a certain derivative. So this is the question is the question he was concerned about is, can you find disks of arbitrarily large size inside the complex manifold? That is Kobayashi hyperbolicity, or lack of it rather. But in any case, the idea is to you ask the question, can you find disks with arbitrarily large derivatives through some points in this maybe compact complex manifold? Now, if you, the problem is now, and not only finding arbitrarily large disks, that's one thing. You also would like to be able to pass the limit and say, if you have arbitrarily large disks, you should have a copy of C. All right, so then the idea is that if you take to pass to a limit, it's not so easy. If you have a sequence of images from on a disk, to pass to a limit, that it might be terrible inside an arbitrary complex manifold. So what you do is you do a rescaling trick, so that in using, I think it's block metric or something, then you can normalize, composing by automorphisms of the disk that puts the point with the largest derivative at the origin. So by some rescaling, you have maps from the disks with larger and larger radius, normalized, say they had derivative 1 at 0, and the derivative is less than or equal to 1 everywhere else. That's because you maximize the derivative at 0. And then you just have uniform convergence. Then it's easy to take subsequences converging, because the derivative of 1 and this is assumed to be a compact space.
So what is the condition to describe this? You can hold this?
The remarkable thing is this argument works in any complex manifold, whatever. Compact complex manifold. That's the remarkable Brody trick.
What do you need to do the argument?
What you need?
What do you need to...
You need, well, I think it's something, well, you have to have a metric here to measure the size of the derivatives. But you start with a family of disks that, say, send 0 in this origin to some point, maybe a variable point. The derivative at 0, let's say the disks have radius r, and but the r keeps increasing. And then maybe you normalize them so that the derivative is 1. Either you normalize the derivative or the radius. So let's say we normalize the derivative to be 1, and the radius keeps increasing. And then you want to be able to pass to a limit so that you can take subsequences, so that in the limit you have a map from C to the complex manifold with the derivative 1. And so you have a sequence of maps from disks of larger and larger radius with the derivative 1 here. But a priori, you cannot pass to a limit because the derivatives might be completely wild out here. So there's no way to pass to a limit. So for that, you take something like the derivative. I think it's, you maximize this function, I think. I might be wrong. But there's something like this that you maximize. So that the derivative, the maximal derivative, becomes, you move that. Let's see, this will make the derivative measure to be 0 at the boundary, so we don't have a maximum somewhere. And this is an invariant under automorphisms of the disks, so you can map the maximum point to the origin. The derivative is then maximized at the origin. And then you can again make that be 1. And then since the derivative is then less than or equal to 1 everywhere, you can take limits. So that's the Brody trick.
So does it tell you that any sequence at all can be renormalized?
Yes. Yeah. 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 It's a completely general theorem about any compact complex manifold. If you have arbitrarily large disks in it, there is a copy of C in it. Completely general. It's quite remarkable.
How do you know that the maximum occurs in the interior of the disk?
Oh, the thing is, well, you can first of all assume that the maps are already holomorphic past the disk a little bit, so that the derivatives are continuous. And then if you use a norm like this, then you put the derivative is considered to be 0 at the boundary, so it will have a maximum on the inside.
So this means if the Kobayashi length of a standard vector is 0, you can find a map of C.
But not necessarily through that point. Because when you do this normalization, even if all those disks you started with went to the same point, after the normalization, this point might be way out at the edge here. When you normalize, and then when you pass the limit, this just disappears in the limit. So we don't know exactly where it is. It might be somewhere else than you thought it would be, but otherwise, yeah. But we are working in some compressed neighborhoods of a given compact, so we know the limit is going to be somewhere in K. Maybe not through the points where we had our disks, but some points. So I guess but to complete this argument, this is so. One possibility is that you have some eigenvalue larger than 1, then you have these copies of C, and you're fine. But of course, if you don't, then the map is actually contracting, because then if you throw out the L's, the expanding factors at each step, the map is actually contracting by a geometric rate. So then, of course, you're down anyway. Then you have an attracting periodic orbit. So that's the argument. So
You're sort of saying you use the C0 closing limit in the holomorphic category.
yeah, right, yeah.
Otherwise, C0 closing limit doesn't have any real use.
Right, we definitely need it, yeah. Because we have to repeat the image of the map. We have to keep repeating the B. Yeah, so I don't know, maybe I'll just stop here instead of moving on, proving other things.
There was already 1 or 2 questions. Are there any more questions?
Do you have any applications of higher dimensional complex analysis systems?
Applications? Oh, I don't know. Not to build bridges or anything like that.
If there are no further questions, let's thank the speaker again.